Jacobians. So, a great German mathematician, Jacob Jacobi, explained Jacobian of functions of two independent variables. Okay, and also Jacobians functions of three independent variables, and in general Jacobians of functions of n independent variables. So first we will explain Jacobian of function of two independent variable. So let u and v be the differentiable functions of two independent variables x and y, then the determinant del u upon del x, del u upon del y, and second row del v upon del x, del v upon del y, this thing, okay, is called Jacobian of u and v with respect to x and y. Okay, and is denoted by del uv upon del x y. Also, this is denoted by j u v, okay, or simply j. So this is the definition of Jacobian of functions of two independent variables. Okay, means if u and v be differentiable functions of two independent variables x and y, then this determinant means this is partial differentiation of u with respect to x, u with respect to y, and here partial differentiation of v with respect to x and v with respect to y. So this determinant is called Jacobian and is denoted by del uv upon del xy or juv. Okay. Similarly, we will explain Jacobian of functions of three independent variables. Jacobian of functions of three independent variables. So similarly, if u, v, and w are functions of three independent variables, functions of three independent variables x, y, and z, then the determinant del u upon del x, del u upon del y, del u upon del z, and in the second row del v upon del x, del v upon del y, del v upon del z, del w upon del x, del w upon del y, del w upon del z. Okay, so This determinant is called Jacobian of functions of three independent variables and is denoted by del u v w upon del x y z or j u v w. Okay, so this is Jacobian of functions of three independent variables u, v and w. Okay, similarly Jacobians of functions of n independent variables. Jacobians of functions of n independent variables. Okay, so Jacobian of functions of n independent variables. So in general, let us suppose if u1, u2, u3 up to un be differentiable functions of n independent variables x1, x2 up to xn, then the determinant del u1 upon del x1, del u1 upon del x2 up to del u1 upon del xn. Okay, so this determinant, and in the second row del u2 upon del x1, del u2 upon del x2 up to del u2 upon del xn. In the nth row del un upon del x1, del un upon del x2 up to del un upon del xn. Okay, so this is the determinant of u1, u2, u3, un with respect to x1, x2, xn. Okay, in first row del u1 upon del x1, del u1 upon del x2 up to del u1 upon del xn, means in the first row we will write partial differentiation of u1 with respect to x1, x2 up to xn. In the second row, partial differentiation of u2 with respect to x1, x2 up to xn. And similarly, in the last row, means nth row, del un upon del x1, del un upon del x2 up to del un upon del xn. So this is Jacobian of functions of n independent variables, means if u1, u2, un are independent variable of x1, x2, xn, then this is Jacobian. Okay, and is denoted by j u1, u2 up to un. Okay, so this is the notation and is denoted by del u1, u2, un upon del x1, x2, xn, or this can also be written as j u1, u2 up to un. Okay, so this is the Jacobian for n independent variables. Now, an example of Jacobian of x, y, z with respect to r, theta and phi means this is an example of functions of three independent variables. Okay, so here x is a function of r, theta, phi, y is a function of r, theta, phi, and z is function of r, theta, phi. Here phi is 1. Okay, so we will calculate Jacobian of x, y and z with respect to r, theta, phi. So as we know, the definition of Jacobian for functions of three independent variables means if u, v and w are independent variables, functions of independent variables of x, y and z, then this is Jacobian. Okay, so first we will calculate partial derivatives. So here, first we will calculate partial derivatives of x with respect to r, theta and phi. Similarly, y and z. Okay, so we have j of x, y, z equal to del x upon del r, del x upon del theta, del x upon del phi. Okay, and similarly in the second row, del y upon del r, del y upon del theta, del y upon del phi, and in the last row, del z upon del r, del z upon del theta, del z upon del phi. Okay, so this is the definition. Now we will calculate partial derivatives, means here del x upon del r. So del x upon del r is theta and phi are constant. So del x upon del r is equal to sine theta cos phi. Del x upon del theta. Del x upon del theta. So here partial differentiation with respect to theta, so r and phi are constant. So here cos theta, r cos theta cos phi, r cos theta cos phi, and similarly del x upon del phi. So del x upon del phi means r and theta are constant, differentiation of cos phi minus sin phi, so this is minus r sin theta sin phi, minus r sin theta sin phi. Okay, now del y upon del r. So del y upon del r, here sin theta sin phi constant, this is differentiation of r is 1, so del y upon del r equal to sin theta sin phi. Okay, so this is sin theta sin phi. Del y upon del theta is equal to r cos theta sin phi. Del y upon del phi is equal to r sin theta cos phi. Okay, similarly here del z upon del r. So del z upon del r is equal to cos theta. Del z upon del theta is equal to minus r sin theta, and del z upon del phi. Okay, so since z is equal to r cos theta, means here phi is absent, so with respect to phi, r and theta are constant, so differentiation of constant is 0, so del z upon del phi is equal to 0. Del z upon del phi is equal to 0. Okay, so now putting the values of del x upon del r, del x upon del theta, del x upon del phi, and all the values. Means now substituting the value of these things here. So we have jxyz is equal to this thing. So by solving, this is a simple determinant of 3 cross 3 order. Okay, so this is equal to sine theta sine phi, sine theta cos phi, and this is 0 into minus minus plus r square sine square theta cos phi, okay, minus r cos theta cos phi. Now this should be 0 minus r sine theta cos phi and minus r sine theta sine phi, and this would be multiplying by minus r sine square theta sine phi minus r cos square theta sine phi. Okay, so this is equal to r square sine cube theta cos square phi plus r square sine theta, here sine theta cos square theta cos square phi, and this is minus minus plus r square sine cube theta sine square phi plus r square sine theta cos square theta, this is sine theta cos square theta into sine square phi. Okay, so now this is r square sine cube theta, r square sine cube theta, so we will take common, so cos square phi plus sine square phi is equal to 1, so r square sine cube theta, this is 1, means cos square theta phi plus sine square phi 1. Now here r square sine theta cos square phi, so plus r square sine theta is common. Now cos square theta, here cos square theta also common, so this is sine square phi plus cos square phi 1. Here again r square sine theta is common, so here sine square theta plus cos square theta, this is 1, so this equal to r square sine theta. So this is the answer. Very important property on Jacobian means theorem first. If the Jacobian of u and v with respect to x and y is J1 and Jacobian of x and y with respect to u and v is J2, then prove that J1 J2 is equal to 1. Okay, so proof is very easy, means we will use the definition of Jacobian of functions of two independent variables. Means we have, if u and v are functions of two independent variables x and y, then Jacobian J1 is equal to del u upon del x, del u upon del y, and del v upon del x, del v upon del y. Okay, and similarly J2 is equal to del x upon del u, del x upon del v, del y upon del u and del y upon del v. Okay, means here J2 is Jacobian of x and y with respect to u and v. Now J1, J2. So J1, J2 equal to multiplication of two determinants, means del u upon del x, del u upon del y, del v upon del x, del v upon del y into del x upon del u, del x upon del v, and here del y upon del u, del y upon del v. Okay, so now multiplication of determinant. So this equal to, this is first row and this is first column. So del u upon del x, del x upon del u plus del u upon, so the multiplication in determinant we have del u upon del x means first row and first column. So del u upon del x upon del u plus del u upon del y, del y upon del u. Okay, here this is first row second column. So del u upon del x upon del v plus del u upon del x, this is multiplication of this second. So del u upon del x into del x upon del v plus del u upon del y, del v upon del y upon del v. Okay, in the second row similarly, second row first column means del v upon del x upon del u, del v upon del y upon del u, and here second row second column means del v upon del x upon del v plus del v upon del y upon del v. Okay, now again we have this thing del u upon del x upon del u plus del u upon del y upon del u. So this is by definition del u upon del u, and this is del u upon del x upon del v plus del u upon del y upon del v, del u upon del v. And here in the second row del v upon del u, here del v upon del v. Okay, so this is del u upon del u 1, del u upon del v 0, because u and v are independent. So here 0 and here 1. So this is 1. Okay, so here we will use definition of total differentiation. Okay, means u and v are functions of x and y. By the definition of total differentiation, this is del u upon del u and this is del u upon del v. Since u and v are independent, so partial differentiation of u with respect to v is 0 and partial differentiation of u with respect to u is 1. So this is very important theorem, means if u, v, w are functions of three independent variables x, y and z, and similarly x, y and z are functions of three independent variables u, v and w, then j, j dash is equal to 1. Means if this is Jacobian of u, v, w with respect to x, y, z, then this is Jacobian of x, y, z with respect to u, v, w means this is j, so this is j dash is equal to 1 or j1, j2 is equal to 1. So proof is very easy. So we will use the definition of Jacobian of functions of three independent variables. So now we have the definition of del u v w upon del x y z. This is equal to del u upon del x del u and del v upon del x del v upon del y del v upon del z. Here del w upon del x del w upon del y del w upon del z. Okay. Similarly, del x y z upon del x del u v w equal to, this is equal to del x upon del u del x upon del v del x upon del w. In the second row, del y upon del u del y upon del v del y upon del w. Okay. Del z upon del u del z upon del v del z upon del w. So now multiplication means del u v w upon del x y z into del x y z upon del u v w is equal to product of this thing. Okay, means we will write here del u upon del x del u upon del y del u upon del z. Here del v upon del x del v upon del y del v upon del z. And in the third row, del w upon del x del w upon del y del w upon del z into del x upon del u del x upon del v del x upon del w. In the second row, del y upon del u del y upon del v del y upon del w. And the third row, del z upon del u del z upon del v del z upon del w. So now we multiply two determinants. Okay, this is 3 by 3 determinant and this is 3 by 3 determinant. Okay, this is equal to first row, first column. Okay, so del u upon del x upon del u plus del u upon del y upon del u upon del z upon del u. This is first row, first column. Similarly, first row, second column means del u upon del x upon del v plus del u upon del y upon del v plus del u upon del z upon del v. First row, third column means in the third step, del u upon del x upon del w plus del u upon del y upon del w plus del u upon del z upon del w. Okay, now in the second row we will write del v upon, this is second row, means del v upon del x. And for the second row, we will multiply second row first column, okay, and then second row second column, second row third column, okay. So second row first column, del v upon del x upon del u, plus del v upon del y upon del u, plus del v upon del z upon del u. In the second step, here second row second column, okay, and here second row third column. This is second row third column. Similarly, in the last row, we will write third row first column. Third row first column means del w upon del x upon del u, plus del w upon del y upon del u, plus del w upon del z upon del u. In the second element, third row second column, and then third row third column, okay. Now we will use the definition. So we get here 1, 0 and 0. Here 0, 1, 0, 0, 0, 1. Because we have, this is the value 1 and this is 0 and this is 0. Because u, v and w, u, v and w are independent variables. It means del u upon del x upon del u, plus del u upon del y upon del u, del u upon del z, plus this is plus. So this is 1 and this is 0 and this is 0, because here u, v and w are independent, okay, and similarly x, y and z are independent. So this is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is equal to 1. Okay, so and is proved. Again, an important property of Jacobians means if u1 and u2 are functions of y1, y2, and y1, y2 are functions of x1, x2, means u1 and x1 are composite function. Okay, so Jacobian of u1, u2 with respect to x1, x2, j del u1 u2 upon del x1 x2 is equal to, first we calculate Jacobian of u1 and u2 with respect to y1 and y2 into Jacobian of y1 and y2 with respect to x1 and x2. So this is very important property, okay. Similarly, if we generalized u1 u2 u3, okay, u1 u2 u3 are functions of y1 y2 y3, and similarly y1 y2 y3 are functions of x1 x2 x3. So this can be written as del u1 u2 u3 upon del x1 x2 x3 equal to Jacobian of u1 u2 u3 with respect to y1 y2 y3 into Jacobian of y1 y2 y3 with respect to x1 x2 and x3. Okay, so this is very easy to explain. Means u1 u2 are functions of y1 y2 and y1 y2 functions of x1 x2. So this is property, and generalization of this thing is this, okay. Jacobian of implicit functions. Okay, so first we will explain implicit function. What is implicit function? So let y is a function of x and fxy. Jacobian of implicit functions. So first we will explain implicit function. Okay, means what is implicit function? So let f is a function of two variable x and y. Okay, means fxy is a function of two variable and y is function of x, such that fx phi x vanishes identically. That is, y is equal to phi x is root of the functional equation fxy equal to 0. Then y is equal to phi x is an implicit function defined by the functional equation fxy equal to 0. Okay, so this is very easy to explain implicit function. Okay, so we will explain Jacobian of implicit functions. Now, theorem on implicit function. If u1, u2, u3 be the functions of independent variables x1, x2 and x3 given by the implicit functions, the following relations means f1, u1, u2, u3, x1, x2, x3 is equal to 0, and second relation f2, u1, u2, u3, x1, x2, x3 is equal to 0, and third relation is f3, u1, u2, u3, x1, x2, x3 is equal to 0. Then the Jacobian, then del u1, u2, u3 upon del x1, x2, x3 is equal to minus 1 to the power 3 del f1, f2, f3 upon del x1, x2, x3 into del u1, u2, u3. In other words, this can be written as divided del f1, f2, f3 upon del u1, u2, u3. Okay, it means if u1, u2, u3 are functions of three independent variables x1, x2, x3, then Jacobian of u1, u2, u3 with respect to x1, x2, x3 is equal to, first we calculate Jacobian with respect to x1 divided by Jacobian with respect to u1, u2, u3. Okay, similarly, if u1, u2, u3 up to n independent function of n variables x1, x2, x3 up to xn, so here minus 1 to the power n del f1, f2, del fn, first we calculate Jacobian with respect to x1, x2, xn, and then divided by Jacobian with respect to u1, u2, un. Okay, so this is Jacobian for implicit functions. Now I will explain some examples on implicit functions. Okay, this is an example on implicit functions. Okay, so here x, y, z, three variable, and here u, v, w means x, y, z are functions of u, v, w, and here we cannot determine the value of x, y, z by these three relations. Okay, it means these are implicit functions. Okay, so first we will write f1 is equal to x plus y plus z minus u equal to 0. Okay, second is, suppose f2, this is y plus z minus uv equal to 0, and third is f3 is equal to z minus uvw equal to 0. So first we u in left hand side we will put this is left hand side, and standard form of f1 is equal to 0, f2 is equal to 0, f3 is equal to 0, means f1 is function of x, y, z and u, v, w. Here v and w are absent, so no problem. f2 x, y, z, u, v, w, f3 x, y, z, u, v, w. Okay, so we have del, then by definition del x, y, z upon del u, v, w is equal to minus 1 to the power 3 del f1, f2, f3 upon del, here in the place of, in the definition, here we have used u1, u2, u3, x1, x2, x3. So in place of u1, u2, u3 is x, y, z, and in place of x1, x2, x3 is u, v, w. Okay, so this is very easy. So here we will write del u, v, w divided by del f1, f2, f3 by del x, y, z. Okay, so this is equal to minus 1 to the power 3 means minus, and this is equal to del f1 upon del u, del f1 upon del v, del f1 upon. So this is equal to, first we calculate del f1 upon del u. So del f1 upon del u is minus 1. Del f1 upon del v, this is 0. Del f1 del w, this is 0. Okay, so we will calculate all the things, which is very simple. So del f1 upon del u is minus 1, 0, 0. Del f2 upon del u, here minus v, del f2 upon del v minus u and 0. Okay, similarly del f3 upon del u, so here minus vw, del f3 upon del v minus uw and minus uv divided by del f1 upon del x. So del f1 upon del x, this is del f1 upon del x, this is 1. Del f1 upon del y, this is 1. Del f1 upon del z, this is 1. And similarly for next, so here del f1 upon del x is 1, 1 and 1. Del f2 upon del x, here 0. Del f2 upon del y 1, del f2 upon del z 1, del f3 upon del x 0, del f3 upon del y 0, del f3 upon del z 1. Okay, so this is equal to minus, now minus 1 into, this is minus minus plus u square v minus 0, and all the terms will 0, divided by, here 1, so 1 minus 0 and all the terms 0, so this is 1. So this is equal to minus minus plus u square v divided by 1 is equal to u square v. So this is answer. Okay, and hence proved. So this is very important theorem. If functions u, v and w of three independent variables x, y and z are not independent, here we see that not independent, then the Jacobian of u, v, w with respect to x, y, z vanishes. Okay, it means del u, v, w upon del x, y, z is equal to 0. So this is important, that Functions UVW are independent variables of xyz, but xyz are not independent. So in this case, Jacobian of UVW with respect to xyz is equal to 0.